The material in question appears to be old electrical metallic tubing, commonly referred to as EMT or thin-wall conduit. In the past, it was a common method employed for electrical wiring installations. However, contemporary electrical standards and practices deem it outdated and potentially unsafe. The primary concern associated with EMT lies in its structural integrity. Compared to other types of conduit, EMT exhibits lower strength and is susceptible to physical damage. This vulnerability can compromise the insulation of the conductors contained within, increasing the risk of electrical shorts and subsequent fires. Furthermore, EMT lacks a watertight seal, rendering it unsuitable for environments with moisture exposure. In such settings, the ingress of water can lead to corrosion and further exacerbate the risk of electrical hazards. Due to these inherent limitations, the use of EMT has been discontinued in modern new construction projects. When encountering EMT in older buildings, it becomes imperative to engage a qualified electrician to conduct a comprehensive inspection. The electrician will assess the condition of the EMT and determine whether it remains safe for continued use or requires replacement with a more robust and code-compliant wiring method. Specifically, concerning the receptacle in question, it is plausible that the EMT was originally installed to extend the branch circuit to the outlet location. Conversely, it is also possible that the EMT was added at a later time, potentially by an unqualified individual. Regardless of its installation history, a thorough inspection by a licensed electrician is crucial to ascertain its safety and compliance with current electrical codes. When assessing EMT, consider several factors. Firstly, inspect the physical condition of the tubing. Look for signs of corrosion, dents, or other damage that could compromise its integrity. Secondly, check the fittings and connections. Ensure that they are properly tightened and that there are no gaps or openings that could allow moisture to enter. Thirdly, evaluate the grounding. The EMT should be properly grounded to provide a path for fault current. Fourthly, consider the environment. If the EMT is located in a damp or corrosive environment, it is more likely to deteriorate. Fifthly, check the ampacity of the conductors. Make sure that the conductors are properly sized for the circuits and that they are not overloaded. Electrical metallic tubing, or EMT, is a type of raceway commonly used to protect electrical wiring. While EMT offers certain advantages, it also presents several disadvantages compared to other raceway options. EMT is generally less expensive than rigid metal conduit, which can make it an attractive option for budget-conscious projects. EMT is relatively lightweight and easy to install, reducing labor costs. EMT is available in a variety of sizes and lengths, offering flexibility in design and installation. However, EMT is not as strong as rigid metal conduit and can be easily damaged by impact. EMT is not watertight unless special fittings are used, which can increase the cost. EMT is not suitable for use in hazardous locations. EMT is not suitable for direct burial unless it is specifically listed for that purpose. EMT requires special tools for cutting and bending, which can add to the cost of installation. EMT is not as resistant to corrosion as some other types of raceway. When selecting a raceway, it is important to consider the specific requirements of the installation. If strength, watertightness, or corrosion resistance are critical factors, rigid metal conduit or another type of raceway may be a better choice than EMT. NEC Article 358 covers the use and installation requirements for electrical metallic tubing. 358.1 scope. This article covers the use, installation, and construction specifications for electrical metallic tubing and associated fittings. 358.10 uses permitted. EMT shall be permitted for both exposed and concealed work. EMT shall be permitted in direct burial applications where identified for such use and installed in accordance with 300.5. EMT shall be permitted in concrete provided suitably protected against corrosion. 358.12 uses not permitted. EMT shall not be used under the following conditions. Firstly, where subject to severe physical damage. Secondly, where protected from corrosion solely by enamel. Thirdly, in cinder concrete or cinder fill unless subject to permanent and effective corrosion protection approved for the purpose. Fourthly, where exposed to chemicals destructive to the tubing. Fifthly, in hazardous locations, except as permitted by other articles in this code. 358.20 size. The size of EMT shall be in accordance with Table 358.20. The trade sizes of EMT are 0.5, 0.75, 1, 1.25, 1.5, 2, 2.5, 3, 3.5 and 4. 358.22 Number of conductors. The number of conductors permitted in EMT shall not exceed that permitted by the percentage fill specified in Table 1, Chapter 9. Cables shall be permitted to be installed where they are identified for the specific use. 358.24 Bends. Number of bends. How measured bends shall be so made that the tubing will not be damaged and the internal diameter of the tubing will not be effectively reduced. The radius of the inner edge of any field bend shall not be less than shown in Table 2, Chapter 9. A combined total of bends plus any offset shall not exceed 360 degrees between pull points, for example, conduit bodies and boxes. 358.26 Supports. EMT shall be securely fastened in place at least every 10 feet. In addition, EMT shall be securely fastened within 3 feet of each outlet box, junction box, cabinet, or fitting. Where structural members do not permit fastening within 3 feet, the distance shall be permitted to be increased to 5 feet. 358.28 Threading. EMT shall not be threaded. Couplings and connectors shall be made uptight so as to prevent electrical discontinuity. 358.30 Securing and supporting. EMT shall be securely fastened and supported in accordance with 358.30. 358.42 Couplings and connectors. Threadless couplings and connectors used with EMT shall be made uptight so as to prevent electrical discontinuity. Locknuts and bushings shall not be used on EMT. 358.56 Splices and tap. Splices and taps shall be made only in boxes, conduit bodies, or fittings that are accessible. 358.60 Grounding. EMT shall be used as an equipment grounding conductor where installed in accordance with 250.118. The NEC specifies that EMT can be used as an equipment grounding conductor if certain conditions are met. The EMT must be installed in accordance with the NEC requirements, including being properly connected to ground. The EMT must be mechanically strong and provide a low impedance path to ground. The circuit overcurrent protection device must be sized to protect the EMT in case of a ground fault. However, it's crucial to understand the potential drawbacks and limitations of relying solely on EMT for grounding. Over time, connections can loosen or corrode, increasing resistance and diminishing the effectiveness of the grounding path. This can compromise safety and increase the risk of electrical shock or fire. For critical applications or where enhanced safety is desired, it is generally recommended to install a separate equipment grounding conductor (EGC) within the EMT. This provides a dedicated grounding path that is independent of the EMT itself, ensuring a more reliable and robust grounding system. The EGC can be a green insulated wire or a bare copper conductor, and it should be sized according to the requirements of the NEC. By installing a separate EGC, you can significantly improve the safety and reliability of your electrical system, especially in environments where corrosion or mechanical damage may be a concern. Always consult with a qualified electrician to determine the best grounding solution for your specific application and to ensure compliance with all applicable electrical codes. Regarding the size and number of conductors permitted in electrical metallic tubing, this is governed by the National Electrical Code and depends on several factors. The NEC specifies the maximum allowable fill percentage for conduits, which is the percentage of the conduit's cross-sectional area that can be occupied by conductors. For EMT, the maximum fill percentage is typically 40% for 3 or more conductors. To determine the appropriate size of EMT for a given number of conductors, you need to consider the following. Firstly, the size of the conductors. The diameter of each conductor, including insulation, must be known. This information is typically found on the conductor's packaging or in manufacturer's data sheets. Secondly, the type of conductors. The type of insulation on the conductors affects their overall diameter. For example, THHN conductors are generally smaller than THW conductors with the same ampacity. Thirdly, the number of conductors. The total number of conductors to be installed in the EMT must be known. Once you have this information, you can use NEC Chapter 9, Table 1 to determine the allowable fill area for the EMT. This table provides the cross-sectional area of different sizes of EMT. You can then calculate the total cross-sectional area of the conductors to be installed and compare it to the allowable fill area. If the total cross-sectional area of the conductors exceeds the allowable fill area, you will need to use a larger size of EMT. Alternatively, you can use online conduit fill calculators, which are readily available and can simplify the process. These calculators typically ask for the conductor size, type, and number of conductors, and then automatically determine the appropriate EMT size. It is important to note that the NEC also specifies minimum conduit sizes for certain applications, such as for equipment grounding conductors. Always consult the latest edition of the NEC and local electrical codes to ensure compliance with all applicable requirements. Proper conduit sizing is essential for ensuring the safe and reliable operation of electrical systems. Overfilling conduits can lead to overheating, insulation damage, and even electrical fires. Therefore, it is crucial to carefully calculate the conductor fill and select the appropriate EMT size for each installation. The National Electrical Code addresses the proper bending of electrical metallic tubing in section 358.24. This section outlines the requirements for making bends in EMT to ensure that the tubing is not damaged and the internal diameter is not effectively reduced. The NEC specifies the minimum radius of bends in EMT to prevent damage to the tubing and conductors. The radius of the inner edge of any field bend shall not be less than shown in Table 2, Chapter 9 of the NEC. This table provides the minimum bending radius for different sizes of EMT. For example, the minimum bending radius for 1/2-inch EMT is 4 inches, while the minimum bending radius for 1-inch EMT is 6 inches. The NEC also limits the total number of bends allowed in a run of EMT between pull points, such as conduit bodies and boxes. The combined total of bends plus any offset shall not exceed 360 degrees between pull points. This limitation is intended to prevent excessive pulling force on the conductors during installation, which could damage the insulation. When bending EMT, it is important to use proper tools and techniques to avoid kinking or flattening the tubing. Conduit benders are specifically designed for bending EMT and can help ensure that the bends are smooth and consistent. It is also important to avoid overbending the tubing, as this can weaken it and make it more susceptible to damage. If a bend is not made correctly, it should be cut out and replaced with a new section of EMT. Proper bending of EMT is essential for ensuring the safe and reliable operation of electrical systems. Improperly bent EMT can be difficult to pull conductors through, can damage the conductor insulation, and can even create a fire hazard. Therefore, it is crucial to follow the NEC guidelines and use proper tools and techniques when bending EMT. Electrical metallic tubing requires adequate support to maintain its position and protect the enclosed conductors. The National Electrical Code outlines specific requirements for supporting EMT in section 358.30. EMT must be securely fastened in place at least every 10 feet. This requirement ensures that the tubing is adequately supported and prevents it from sagging or shifting over time. In addition to the 10-foot rule, EMT must also be securely fastened within 3 feet of each outlet box, junction box, cabinet, or fitting. This requirement provides additional support at termination points, where the tubing is more likely to be subjected to stress. In situations where structural members do not permit fastening within 3 feet of an outlet box, junction box, cabinet, or fitting, the distance is permitted to be increased to 5 feet. This exception provides flexibility in situations where it is difficult to comply with the 3-foot rule due to physical obstructions. EMT must be supported using approved methods, such as straps, clamps, or hangers. The supports must be designed to securely hold the tubing in place and prevent it from moving or vibrating. It is important to use the correct size and type of support for the EMT being installed. Over-tightening the supports can damage the tubing, while under-tightening them can allow the tubing to move. The NEC also prohibits the use of certain types of supports that can damage the EMT, such as wire or cable ties. Proper support of EMT is essential for ensuring the safe and reliable operation of electrical systems. Inadequately supported EMT can sag, shift, or become damaged, which can compromise the protection of the enclosed conductors and create a safety hazard. Therefore, it is crucial to follow the NEC guidelines and use approved support methods when installing EMT. Electrical metallic tubing connections need to be properly made to ensure electrical continuity and mechanical strength. The National Electrical Code outlines specific requirements for connecting EMT in Section 358.42. EMT cannot be threaded in the field. This is because threading weakens the tubing and can make it more susceptible to damage. Instead, EMT must be connected using threadless couplings and connectors. Threadless couplings and connectors are designed to provide a secure and reliable connection without the need for threading. These fittings are typically made of steel or aluminum and are available in a variety of sizes and types to accommodate different applications. Threadless couplings and connectors must be made uptight to prevent electrical discontinuity. This means that the fittings must be tightened securely to ensure a good electrical connection between the EMT and the fitting. Loose connections can create resistance, which can lead to overheating and even electrical fires. Lock nuts and bushings are not permitted to be used on EMT. Lock nuts are typically used to secure conduit to boxes or enclosures, while bushings are used to protect conductors from abrasion. However, these fittings are not designed for use with EMT and can damage the tubing. When making EMT connections, it is important to use the correct tools and techniques. Conduit wrenches are specifically designed for tightening threadless couplings and connectors and can help ensure that the fittings are properly tightened. It is also important to avoid over-tightening the fittings, as this can damage the tubing. Proper EMT connections are essential for ensuring the safe and reliable operation of electrical systems. Improperly made connections can create electrical hazards such as overheating and electrical fires. Therefore, it is crucial to follow the NEC guidelines and use approved fittings and techniques when making EMT connections. Electrical metallic tubing splices and taps within EMT systems require careful attention to ensure safety and compliance. The National Electrical Code addresses these requirements in Section 358.56. Splices and taps in EMT systems are only permitted in accessible locations. This means that the splices and taps must be located in boxes, conduit bodies, or fittings that can be easily accessed for inspection and maintenance. This requirement is intended to prevent hidden splices and taps, which can be difficult to locate and repair if they become faulty. The boxes, conduit bodies, or fittings used for splices and taps must be of sufficient size to accommodate the conductors and connections without overcrowding. The NEC specifies the minimum size of boxes and conduit bodies based on the number and size of conductors. It is important to select the correct size of box or conduit body to ensure that the conductors are not damaged or subjected to excessive stress. All splices and taps must be made using approved methods and materials. This includes using properly sized connectors that are listed for the specific type of conductor being used. The connectors must be installed according to the manufacturer's instructions to ensure a secure and reliable connection. The NEC prohibits the use of certain types of splices and taps, such as open-air splices and Tate splices. These types of splices are not considered to be safe or reliable and are not permitted in electrical installations. After making the splices and taps, the conductors must be properly insulated and protected. This can be accomplished by using insulated connectors, tape, or other approved methods. The insulation must be rated for the voltage and temperature of the circuit. Proper splices and taps are essential for ensuring the safe and reliable operation of electrical systems. Improperly made splices and taps can create electrical hazards such as overheating, short circuits, and electrical fires. Therefore, it is crucial to follow the NEC guidelines and use approved methods and materials when making splices and taps in EMT systems.